Welcome to another lesson in the Designing VMware Infrastructure video training series. The topic and title of this lesson is Defining a Logical Compute Design. In this lesson, we'll start out by defining what it means to define a logical compute design. What does a logical compute design include? And what are some of the values and how they're expressed in a logical compute design? Next, we'll get into a more detailed discussion of how we go about determining the values that should be specified in a logical compute design. Third, we'll look at some example logical compute designs and the values that were used to both calculate those logical compute designs and the values specified in the logical compute designs. And then finally, we'll round out this lesson with introducing the topic of examining related areas. This is a topic that you'll see recur in other lessons in this course as we begin to look at relationships and dependencies between various areas in the design in an effort to continue to maintain our holistic view of the design, a key part of being an effective vSphere architect. Let's start out with a discussion of what it means to define a logical compute design. What does a logical compute design mean? What does it include? Recall from other lessons in this course that a logical design is a high-level abstract design that does not specify particular products or solutions. And therefore, in the logical compute design, you're simply going to be specifying things like aggregate CPU capacity, which you would typically express in gigahertz, aggregate RAM capacity, like you would specify typically in gigabytes or perhaps even terabytes, your socket to core ratios and target core to VM ratios, and some description of the expandability of the logical compute design. While you typically will not include particular products, solutions, brands, or models, you may specify in the logical compute design particular technologies. For example, you may say that the underlying CPU should support hardware virtualization extensions. That would be an example of saying that the logical compute design needs to have a specific function, but you're not being so specific as to say it must support Intel nested page tables, for example. All of these things roll into the logical compute design. Some things you don't see listed here in this discussion of the logical compute design include things like the number of clusters that we will use, the size of the clusters, use of resource pools, or even the use of a separate cluster to host the infrastructure management components for the design. All of these things have been moved into a separate lesson in this series where we can discuss them in detail and help provide a better understanding of the impact on the design of these various design choices. The logical compute design, as you can see, has these aggregate values that you have to include, but how do we go about determining what aggregate values we actually specify? Aggregate CPU and RAM capacities are two of the things that you have to specify in the logical compute design. But how do we determine what values should be specified here? These capacities actually should have been defined or will be defined during your requirements analysis. And they're going to be based on data that you obtained during the information gathering process. Recall that in another lesson in this course, we talked about the process and the procedure for gathering information in order to be able to define the design factors. Those design factors being requirements, risks, assumptions, and constraints. And among the requirements are functional requirements, such as I have to be able to support a certain amount of CPU capacity, I have to be able to support a certain amount of RAM capacity. So your aggregate CPU and RAM capacities are actually driven straight out of the requirements analysis based on data provided by tools that assess the current environment or that assess the applications, operating systems, services, and workloads that are anticipated to run in the environment. A variety of tools can help you get that information. We discussed in other lessons in this course tools like Capacity Planner, VMware's hosted assessment service, operating system specific utilities like Performance Monitor on Windows, or other management and utilization tools both from VMware and third-party organizations. All of these will provide the data during the information gathering process that will help you define the requirements and other design factors, and out of those will come also your aggregate CPU and RAM capacities. Looking at the specific calculation on how we determine some of these numbers, there's a number of different pieces that go in here. So how we determine the logical compute design, first of all, we have the aggregate requirements, which as you just saw are driven by the functional requirements and are defined in the requirements analysis phase based on information gathered during that phase. You're also going to bring to bear information like your desired maximum utilization thresholds. How far do you want to push the environment? Do you want to go to 70% utilization? Do you want to go to 80% utilization? Do you want to go to 90% utilization? What is the anticipated growth in the environment, if any? I personally would find it unusual not to build anticipated growth into the design, but there may be use cases out there where it's a fairly flat environment, and once the workloads are in, they're not anticipated to grow. And in some cases, you may also need to factor in the anticipated virtualization benefit, if any. For example, when we're talking about aggregate RAM capacities, there is a potential virtualization benefit that comes out of VMware vSphere's memory sharing technologies. With these sort of values in mind, what I'd like to do at this point is delve into some example logical compute designs and sort of dissect them and see the numbers that were used and how we came to the projected numbers in those logical compute designs. In this first example, we're taking a look at a table that's taken from the Cloud Infrastructure Architecture case study. This is the document that I reviewed with you in another lesson in this course that provides an example of what a design document should look like. In this particular table, we're looking at values that were gathered during an assessment of the existing environment. If you go and look at the text in the Cloud Infrastructure Architecture case study, you'll find that the text of the document actually specifies that VMware's Capacity Planner tool was used to gather this data. But as you can see here in this table, the information that was gathered and here is being presented is stuff like the average number of CPUs per physical system, the average CPU capacity specified in megahertz, the average CPU utilization both at peak and just at average. Interesting side note here, you can see that the average CPU utilization here is about 12%. That's actually higher than the industry average, measured often below 10%, sometimes as low as 6%. The peak utilization you can see here is much higher at 36%. But using these numbers, and we don't have a total on how many systems were actually measured here, but using these numbers and taking the average peak, we can arrive at a total aggregate CPU capacity of 202,000 megahertz or 202 gigahertz total CPU capacity. And that's our functional requirement. That's where we arrive at the point where we say we know that the environment has to be able to drive at least 202,000 megahertz of CPU cycles. And we'll use that as we go about deriving other values in the logical compute design. In the same manner, we take a look at the RAM statistics that were gathered, average amount of RAM per system, average and peak memory utilizations, total RAM, and then here we see an example of assumed virtualization benefit, memory sharing benefit of 25%. You'll note the asterisk there. The text of the document specifies that this number is deliberately kept low because the design assumes, keep in mind we have design factors, assumptions here, that guest operating systems running in this environment will leverage large page tables. And large page tables typically will result in a lower memory sharing benefit. Putting these numbers together, and again, we don't have a total on the number of systems that were analyzed, we arrive at an aggregate RAM requirement of 206,000 megabytes or 206 gigabytes of RAM. Continuing on looking through here, based on those values, those aggregate CPU and aggregate RAM capacities, we can then go in and say, okay, how do we determine what the logical design is going to look like? Here we have some numbers that are suggested in the actual design process, and depending on the tool that you use, there may be some what-if scenarios that you can run. You may run through a couple of different scenarios until you find what we often call the sweet spot. That sweet spot being the number of sockets or the number of physical CPUs in the host and the number of cores per CPU. In this particular case, as is quite often the case, the sweet spot proves to be a dual socket host, and in this particular case they're specifying 8 core CPUs, so we're talking about 2 sockets with 8 cores per CPU. You'll note in this table that they specify AMD here. That's because the requirements and assumptions and constraints earlier in the Cloud Infrastructure Architecture case study, where these tables are taken, specifies that AMD CPUs will be used. Then we show the number of megahertz per core, the total number of megahertz per CPU. That's simple math, 2300 megahertz times 8. And then we look at total megahertz per host. That's the number of cores times the number of sockets, 2. We double that number. And then here's where our proposed maximum utilization comes in. This particular design says we're going to propose a maximum of 80% utilization. So 80% of that 36,800 megahertz comes to 29,400 megahertz. That number represents the maximum amount of CPU cycles that any given host in this design can contribute. By the same token, we take a total of suggested RAM, in this case 96 gigabytes of RAM, and a proposed maximum host RAM utilization of 80%, and we arrive at a figure of 76,800 megabytes or 76.8 gigabytes of RAM being the maximum threshold that a particular host can contribute. So what we have now, thus far, is we have an aggregate value for both CPU and RAM, and we have values that are representing the maximum amount each given host can contribute. When we combine those numbers together, we can arrive at an estimate of how many hosts are going to be required. So bringing over the 202,000 megahertz and 206,000 megabytes of CPU and RAM, and then dividing those numbers by the maximum CPU threshold and maximum RAM threshold, we arrive at the number of ESXi hosts that are required in order to satisfy those functional resource requirements. In this particular case, the higher of the two numbers is selected because we can't, even though we can get by with only 3 hosts for RAM, we would not be able to satisfy the CPU requirements. So we have to go with the 7 hosts required to satisfy CPU requirements. And in the lower table, you see that we factor in the growth, we factor in the availability requirements. Here, the availability requirements are specifying N+1, which means we have a spare server for failure. We can still satisfy the resource requirements even if one host fails. And we arrive at a total number of ESXi hosts, the value being 10. So you can see, walking through these examples, these tables, we take the aggregate CPU and RAM capacities, we factor in our socket to core ratios, how many sockets, how many cores, our maximum utilization, our anticipated growth, and then we can arrive at a value that says this is about how many hosts are going to be required in order to support the functional requirements as they've been gathered and defined earlier in the design process. Now, there are other factors that might contribute to this. You might have factors that contribute to it, like operational ownership. For example, if the workloads in this particular environment might be operated or managed by 2 different environments, you might have to split this into 2 different clusters or 2 different groups of servers, and therefore your availability requirements and growth percentages might end up looking different. You might end up having to do 12 hosts instead of 10, something of that nature. So this gives you a good idea of the general process, but you're also going to have to take a look, again, maintaining that holistic view of the environment. And speaking of holistic views, that leads us into our next topic, which is examining related areas. The whole idea behind examining related areas is asking ourselves questions like, what does aggregate CPU capacity affect? And then being able to describe or list all of the other areas that are impacted or affected by changes in aggregate CPU capacity. I have 2 examples here. For example, the ability of the design to satisfy functional requirements. If I don't specify a large enough value for aggregate CPU capacity, then the design will be unable to satisfy the functional requirements. It will be unable to provide enough aggregate CPU power to drive the applications, operating systems, and workloads that are specified to run in this. Aggregate CPU capacity also affects the financial constraints. Recall that in another lesson in this course, we talked about how pretty much every project is going to have financial constraints because every organization ends up with having a budget, and therefore specifying too much aggregate capacity might exceed the budget for the project. We might be not adhering to the financial constraints that have been put before you in this particular project. Similarly, changes in aggregate RAM capacity affect the ability of the design to satisfy functional requirements. Licensing, as you know, vSphere 5 adds a memory tier in the licensing. So as you specify larger values of aggregate RAM capacity, you may run into changes in licensing. That in turn, along with just the cost of the RAM, could affect the financial constraints. What about socket to core ratios? Why does it matter if we specify 2 sockets and 4 cores per CPU or 2 sockets with 8 cores per CPU? Well, there's licensing. It's currently licensed based on the number of sockets. Also, the socket to core ratios will affect your target VM to core ratios. how many VMs are you hosting on a particular CPU core, and how will target VM to core ratios that are too high affect the ability of the design to satisfy the performance requirements, meet SLAs or SLOs, for example. It'll also affect physical form factors. If I specify that I want 4 sockets with 4 cores each, well, that's a different kind of form factor. Some blades may not support 4 CPUs. You may have to go to rack mount servers. And then that will in turn affect a whole host of other things as well. What about expandability? Well, of course, that's going to affect the ability of the design to satisfy the functional requirements. In other words, future growth. If you don't specify enough expandability, then the environment can't grow enough. And based on the particular product or solution that you map into this logical design, that could also affect the financial constraints. Now, while listing them here and asking this sort of question and answer format is one way of exploring the relationships, I'd like to introduce you to a different way that involves a more graphical view of relationships. Here on this slide, you see I've created a mind map. A mind map shows relationships between topics and ideas. And I have found a mind map to be a great way of exploring relationships between different areas in a design. So for example, you can take your one area like the logical compute design and then list all the areas that are affected or that are included in a logical compute design. In this particular case, I've listed the 4 topics that we discussed in this lesson: aggregate RAM capacity, total number of sockets and cores, expandability, aggregate CPU capacity. And then from there we delve into what is affected or what can be affected by this particular metric. If I change aggregate RAM capacity, what will be affected? If I change total number of sockets or total number of cores, what will be affected? If I change aggregate CPU capacity, what will be affected? And then from there, you could even take it farther and say, well, if this is affected, then what else could be affected? Theoretically, you could go multiple levels upon multiple levels in this particular manner, but realistically, after a few levels, you'll get a pretty good idea of how things are related to each other. This is one way of exploring related areas. This is a tool that I use, and this is a tool that I'll show in other lessons in this course as we move through both logical and physical designs in the various lessons in this course. There are a variety of tools that you can use to create mind maps, both free and paid applications. I'll leave it as an exercise to the reader to find the application that works best for them, or to experiment to see if something like mind mapping is even a tool that will work for you as a vSphere architect. As we wrap up this lesson in the Designing VMware Infrastructure training course, what we took a look at in this particular lesson was first what it means to define a logical compute design. What are the metrics and values that need to be included in the logical compute design? We then went into a discussion of how we go about determining the values that are specified in the logical compute design. We then used an example from the Cloud Infrastructure Architecture case study to walk through creating the logical compute design to see what numbers are involved and how these numbers are related to each other and coming up with the final recommendations. And finally, we take a look at examining related areas, maintaining our holistic view of the design, not just being focused on compute, but understanding that choices and values specified in the compute design will have ripple effects on other parts of the design. This is an area that we will revisit in other lessons in this course as we continue to reinforce the idea of maintaining a broad holistic view. And that wraps up this lesson. Thanks for watching.